Okay. So what we're going to do today is we're going to spend a little bit of time, probably the first hour, working on Chapter 5 materials, and then we'll stop about 10 o'clock and move to any questions you might have for the exam review. One of the classmates has already reached out about resonance, so we'll definitely, I'll put it on my list over here. Resonance will cover a little bit as well. So my handwriting is going to be a little bit different today because I decapitated my knuckle with a cheese grater. So, and I'm right-handed, so it's going to look kind of funny on the screen. And this is my husband's fault, so it's not that I can't do it. Okay, so let's go. Oh, I got to plug it in first. Really is his fault. Like, I'm not just absent-mindedly blaming him. Okay, all right. Let's get this in. Okay. So we had, sorry, my cat started playing with the model kit, so I had to make sure I still had them. So we had ended by starting to talk about what happens when you have a set of molecules that with a mirror plane will be mirror images or reflections of one another. But if you physically take one of the molecules and try to overlap it on the other, the best you're going to be able to do is line up 2 of the 4. Okay, so there's no way, with the exception of a chemical reaction, that you can make these compounds the same. Okay, so this is going to be molecule A. This is going to be molecule B. Okay. So you can't take A to B without a reaction. So if you just have molecules floating in a solvent, A will never overlap with B. Okay. So these molecules, A and B, so A and B are a pair of enantiomers. They're 2 similar but different compounds. Oh gosh, sorry y'all. There we go. Okay, in terms of their similarities, they're going to have the same formula. Okay, they're going to have the same, they're not constitutional isomers of one another. So they have the same bonding arrangement in terms of Lewis structures, if you were just going to draw them out. But they differ in their 3-dimensional spatial alignment or spatial arrangement. Okay. So if you drew it flat as a Lewis structure, you could have green, blue, red, yellow. Okay, but it's only when you take it into the 3 dimensions that you're going to end up with a pair of enantiomers. Okay. When you have compounds that are related in that way, They're called stereoisomers. Okay, so they're not constitutional isomers, they're stereoisomers. Okay. The carbon here is bonded to 4 different groups, and it's sp3 hybridized. Okay. When you have the same formula, same bonding arrangement, what you're going to end up with, I need to add some more stuff in here, is that they're going to have the same intermolecular forces. So they're going to have the same physical properties. So they're going to have the same melting point, the same boiling point, the same behavior on a separation column, same dipole moment. They're going to have the same solubility in solvents. But because they're different compounds, they're going to behave differently in what we're going to call a chiral environment. Okay. So your body is a chiral environment. So the example that we talked about in the discussion was thalidomide, but Zyrtec is another example. Albuterol, which is an asthma inhaler, is another medication that comes as a pair of enantiomers. So in the case of albuterol, one of the enantiomers is going to unlock a mechanism to reduce the swelling or the inflammation in your lungs, in the bronchial tubes. The other enantiomer unlocks a lock and key mechanism that in children can cause like extreme hyperactivity. So you have a couple of different reactivity outcomes based on which of the enantiomers that you pick or that you're using. Okay, so again, we're going to practice drawing these, but we first are going to practice how to pick out that chiral carbon. So if you find an sp3 carbon in your molecule, you need to check to see if it's chiral. So that word chiral would imply 4 different groups. Now what you're going to start seeing a lot of is the wedges and dashes on carbon atoms. So for example, if we look at the first on the slides, this is the molecule that's shown. Okay. Now, when you should still be able to name this, but we're going to have to add in a new designation because we have to name the 2 enantiomers different from one another. Okay, so in this particular molecule, you have 4 sp3 carbons. Okay. But only one of them is bonded to 4 different groups. So if you draw out this hydrogen, this carbon here with that's now the dot has a chlorine, a hydrogen, a 2 carbon group, which is an ethyl, and a 1 carbon group, which is a methyl. Okay, so even though this is a CH3, and this is CH2CH3, they're different. Okay. So this carbon in the middle here is chiral. Now, when you would name it, you're going to have a designation, which we'll talk about what's going to go in the box. And this compound would be 2-chlorobutane. So you're not going to name it with the methyl and the ethyl groups, because you still have to find the longest carbon chain, which is going to include both this left-hand side and the right-hand side. All right, so the next one on the list, or on that slide, 2, 3, 4, 5, 6, has an OH here. So this is an alcohol. Again, this is the chiral carbon, even though all of these carbons are sp3 hybridized. You have, this is called a hydroxy group. And you would have the hydrogen here. Okay, so you would have a hydrogen, a hydroxide, or a hydroxyl group, 2 carbon group here, which would be ethyl, 1, 2, 3 carbon group here, which would be propyl. Okay, now you don't really need to know how to name alcohols, but they're not terribly difficult. And again, we'd have to have a designation that'll be put in this box. There's 2 different ways to name alcohols. You can use the hydroxy substituent, like 3-hydroxyhexane, but the other way you could write this would be 3-hexanol, because a 3rd carbon contains the alcohol group. Now the last one, and then I'll show you an example when it isn't chiral, is if you take a ring, and we'll just put a bromine on top of the ring. Okay. Now in this case, not all of the carbons are sp3 hybridized. This carbon here and this carbon here are only sp2 hybridized. These carbons are missing 1 hydrogen, whereas these carbons are missing 2 hydrogens. So when you have a situation where you have a ring, what you need to do is go around the ring in both directions. Okay, so if you come out to this side to see what that carbon is bonded to, you would find out that it's bonded to an sp3 carbon. Whereas if you come down this side, you find the sp2 carbon. So since those are not the same, because of the number of hydrogens involved, those 2 carbons are not equivalent, and so you end up with your 4 different groups. Now, in the absence of that pi bond, things are a little bit different. If you drew it like this, but left off the pi bond, then what you would have to do, and you can convince yourself of this, is when you go around both sides, this way and this way, you have an sp3 and an sp3. Down here, sp3, sp3, so they're still the same. And then when they get to this position, they share. Okay, both sides come to that shared position. So in this case, the carbon would be achiral. You can have a chiral compound with a chiral carbon. You can have an achiral compound with an achiral carbon. So just adding that A just means not. Okay, so we're going to take this first one, the 2-chlorobutane, and do a little bit more work on it, unless there are any questions. So what we're going to do on this slide is we're going to practice the 2 ways to draw a pair of enantiomers. The compound on there actually is a little bit longer. It's 2-chloropentane, but it's the same idea. Okay, and so we're going to put chlorine here. Okay.
And again, it's always nice at the start to remember to draw your hydrogen on the dash. And remember that a CH3 methyl is not equivalent to a CH2, CH2, CH3 propyl. So there are two ways that you can do this. The first is to use a mirror. Okay. And when you use a mirror, you're going to have to draw the reflection. Okay. So I'm going to use this blue line here to represent my mirror. And then I'm going to use a couple, if I can find some, a couple different colors on those carbons. Okay. So purple, red, blue, green, orange. Okay. Now with this mirror plane, you can go ahead and draw the 5 carbon reflection. But when you do the reflection, the purple is going to end up closest to the mirror. Then red, blue, green, orange. Okay. When you draw the other enantiomer and you use reflection, you do not change the dashes and wedges. You leave them as they're drawn, but on the same carbon. So on this carbon here, the green carbon, you have a chlorine on a wedge, so that over here, this green carbon has to have chlorine on a wedge. Okay, so you can't change the dashes or the wedges. Okay, I'm going to redraw the molecule down here. Okay. Right. The second way is keep the chain. Okay. And what I mean by keep the chain is we had colored these purple, red, blue, green, orange. And when you keep the chain, you keep that same order. So orange was at the left side, orange is still here on the right side. I mean, sorry, on the left side. Then green, blue, red, purple. Okay. Now, if you keep the chain, you must change dash and wedge. Okay. So when you find your green carbon here with a wedge chlorine, over here it becomes a dash chlorine. The dash hydrogen on the left becomes a wedge hydrogen on the right. Okay. Now, if I were you, I would pick one way or the other. I wouldn't mix them up. I would either say I'm going to use A and always use A, or use B and always use B. Okay, so pick a way that works better for you. Now, the thing about these images that we've drawn are these two here are enantiomers. these two here are enantiomers. These two are the same molecule. I can go from here to here by taking like a spatula underneath this molecule and flipping it over to the right. If I flip this over, then the chlorine is going to go from the left side on a dash to being on the right side on a wedge. Okay. So these are a pair of enantiomers, and these are a pair of enantiomers. They're not the same molecule, so they need different names. So they need to be distinguished within the name. Okay, are there questions before we move on and learn the rules for naming? Okay. All right, so clean up my marker situation here. So this is section 5.3. And in 5.3, we're going to designate nomenclature. So that's the name. So designate the name using what are called the con, prelog, oh wait, con, Ingold, sorry, I gotta have them in the right order. Con, Ingold, prelog rules, or the CIP. Okay. The first rule, pretty straightforward. You have to find your chiral compound or your chiral carbon. Okay. And remember, the chiral carbon is sp3 with 4 different groups. And when I say groups, it could be an atom like hydrogen, fluorine, bromine, and iodine, or it could be 4 different alkyl groups. It could be a combination. So as long as they're different, they count. Okay. The second rule is you're going to look at the 4 groups. Off your chiral carbon and assign priority.
You're fine to use Wi-Fi and stuff. I fixed it.
Okay. So priority is going to be given 1, 2, 3, 4. Okay. The 1 group is the highest priority. Four is the lowest priority. Okay. The way that you rank these is based on atomic number. So the highest priority will be the atom with the highest atomic number. Lowest priority will be the lowest atomic number. Now, sometimes when you do this, you're going to find that if the first atom off the chiral carbon cannot distinguish priority, then you must look at other atoms in the group. And I'll show you how to do that. I've got, let's see, 3 more rules left. So does anybody need me to slow down or give them more time on this slide? Okay. The 4th rule, and we'll go through all of these so and practice. The 4th rule is if the group, or if a group, contains a multiple bond, so either a double bond or a triple bond, the atom counts twice.
Did you throw away my top to my orange juice?
Okay, so the 5th rule is that after you've done this, you end with a carbon with the 4 groups ranked. Okay. All right, so you're going to have to move.
Thank you.
Or reorient your molecule. So literally move it in 3-dimensional space or in your brain. You're going to have to reorient the molecule so that number 4 priority is on a dash. Okay. So what you're going to do is you have to kind of pretend that this is a person driving a car. Okay, and they have a steering wheel, and then they have the steering column. Oops. The steering column is number 4. So what the person is going to look at is going to be the steering wheel. And then what goes behind the steering wheel is number 4. So you're looking at your steering wheel. Okay. And then there are only 2 ways, 3 things, we'll show the 3 priority groups, can sit on the wheel. Okay, so they're either going to be 1, 2, 3, and then 4 would be at the back, or 1, 2, 3. Okay, it's either or. Okay. Once you have it oriented, then what you're going to do is you're going to connect 1 to 2, 2 to 3, 3 back to 1. Over here, 1 to 2, 2 to 3, 3 to 1. Okay, and then you put your hands on that steering wheel, that circle you just made, and you turn in the direction that the arrows are pointing you. So this one is going this way, clockwise, which is turning to the right. So this orientation is called R. Okay. This one is going this way, which is counterclockwise. but it's not given an L. Okay, it's given an S. Okay, so the reason that that is how you do this, or why it's given an S, is that, you know, a long time ago, people who were left-handed were considered to be witches and evil. So S stands for sinister, turn to the left. If it goes to the right, you just give it a regular R. If you have the slides in front of you, the next slide just shows you reorienting the molecule and then comparing these diagrams to steering wheels. Okay. Are there questions before we do some practice? Okay. Perfect. Right. All right. So let's go back to, yeah. Okay. So, and if you want to, you can start drawing some little bits and pieces on the alkyl chains. Because first you have a carbon and here you have a carbon. Okay, so our chiral carbon is this one with the dot. Okay. If you have a hydrogen, hydrogen is atomic number 1, so it'll always be group 4. And in this particular case, it's already on a dash, so it's in the right position right from the start. Okay. Chlorine has a higher atomic number than carbon. Carbon atomic number is 6, chlorine is 17. So the chlorine gets priority 1. Okay. Now when you come to distinguish these two groups, this carbon atom is atomic number 6. This carbon atom is atomic number 6. So these first atoms that are connected to the chiral carbon cannot be distinguished because they share the same atomic number. Okay. In order to break the tie, you look at the number, the atoms that this carbon is connected to, but you cannot recount the chiral carbon. So this carbon over here is a methyl carbon. So it's bonded to hydrogen, hydrogen, hydrogen. So each one of those 3. This carbon in the propyl chain is bonded to 2 hydrogens and this carbon. Okay. Then you compare these groups. This carbon atom is a 6, and you play your strongest card first, like you play your highest atomic number. This carbon beats a hydrogen. So this becomes 2, and this is 3. It has nothing to do with the weight of the group. It has to do with the atomic number of the atoms in the group. So now we have our priorities listed: 1, 2, 1, 4, 2, 3. And you would move the molecule so that 4 is in the back. Then you connect. 1 comes down towards 2, 2 to 3, 3 to 1. Okay, and when you rotate in the direction the arrows point, you get R. So, oops, let me just turn off that light. So this compound is R 2-chloropentane. Now it's 2 bar. Are there questions about that example? Yeah. Why did you say LO? Oh, the sinister. Oh, yeah, that's hysterical. It gets me every time. Okay. All right, let's do another one. All right, now this one I'm going to draw a little bit differently. You don't have to color in your wedges. Most of the time I don't, but because these markers are easy to work with, it's kind of fun. Okay. All right, so our chiral carbon is this carbon here, because it has a hydrogen. Oops, that's supposed to be a methyl, CH3. Okay, hydrogen, methyl, ethyl, hydroxide. So those are 4 different groups. In this case, as always, if you have a hydrogen, it's 4. Okay. Oxygen, carbon, carbon. The atomic number excuse me, of oxygen is 8. Carbons are 6, so that's a 1. Okay. Now, let's pretend we hadn't just done this because we know that, kind of already know the result. Carbon is tied with carbon. So both this carbon here and this carbon here have atomic number 6. This carbon is bonded to 3 hydrogens. This carbon is bonded to 2 hydrogens, and this carbon. Carbon beats hydrogen, so this is 2, this is 3. Okay. Ignoring 4 since it's on the dash. 1 to 2, 2 to 3, 3 to 1. So this is S, it has 2 names, 2-hydroxy butane, or you could call it S2-butanol. Are there questions about that one? Because now what we're going to do is we're going to put the hydrogen on a non-dash bond.
Yeah, I have a question.
And add in a multiple bond. And then I'll give you some practice.
I have a question.
Okay.
Just.
I think there's a question.
Hydrogen. Oops.
Yeah, I have a question. Can you guys hear me? Yeah, I don't know.
I can hear you.
That's good.
We can hear you.
Okay, yeah. My question was, why did you get 2? Why did you put
You're
the
talking
number
about
2?
each other. Ooh. Oh, people have questions. Okay, well, you either have to unmute yourself.
What?
Or
I am
text them,
unmuted.
'cause I
Can
can't
no one
hear you.
hear?
Someone is asking you a question.
I
Okay,
can hear you.
so
but I
if
don't
you're
think-
the person who has a question, I can't. Okay, all right. If you are SMS2452, I need you to text your question through the chat feature, or somebody else tell me what she's asking, or she or he. I can't. So.
Can you hear me?
Okay, why did you put the number 2? Oh, with the ethyl group. Let me draw it like this. Okay, so this is 1 and 4. Okay, so is everybody 2, 4, 5, 2? I know I come up as EAM Walters. It doesn't show my name, but so I don't understand why some of you get to have your names and some don't. But 1 and 4 should be clear. Okay. So then what you do is you come up to this carbon and you have to distinguish it from this carbon. So you have to look at the 3 things these carbon atoms are bonded to, but you cannot count the chiral carbon. So this carbon is making 1, 2, 3 bonds to hydrogen. So you write hydrogen, hydrogen, hydrogen. Okay, why did I think it was methyl when you drew the line bond drawing? Down here? Annie, down here? Oh, because if this is a CH3, then that carbon would have, yeah, that's right, mixed, right. If you tried to have 3 hydrogens here and the connection to the chiral carbon and the connection to the end methyl, you would have a 5 bonded carbon, and that would exceed the octet. Okay. So then this carbon here, you have to look at what 3 atoms this carbon is bonded to, but you can't count this one. So this is like the, I don't know, this is like the castle that they're fighting over. So they can't play that castle. They have to play their army is the other stuff that's involved in the end part of the bond. Okay, so this carbon is bonded to these 2 hydrogens and this carbon. Okay, so it's kind of like when you're playing war, like with the card game, except you can cheat. Okay, so you have a hydrogen, hydrogen, hydrogen versus hydrogen, hydrogen, carbon. And since carbon beats hydrogen, this whole group becomes 2, and by default, this one 3. Okay. So does that answer the original question about why this ethyl group is 2? Okay. Okay, so then it sounds like Andrew had a question that I couldn't hear. Andrew, can you type the question? Or was your question answered in that? Okay. Were you just swearing about this and everybody could hear you but me? Okay. All right. All right, so then the last one I'll do with you, and then I'll give you a practice. Let's see, okay. Oh, the name of that last, that's so weird. Okay, the name of that last compound was S2-butanol. Hang on a second. This person never calls me. This could be emergency. Hello? Yes, ma'am. Hey, I'm good. I'm good. I'm teaching a class online right now. Is everything okay? Okay. Okay. Okay, that sounds perfect. All right, thank you, Gwen. Yeah, bye. Okay, so that's 2-butanol. Okay. Right. And then like that. So this looks pretty weird. Okay. All right, so this carbon here is the chiral carbon. Has a hydrogen, a chlorine, a methyl, and then this is called a methylene. Okay, so the chlorine has the highest atomic number, so it's priority 1. Hydrogen has the lowest atomic number, it's priority 4. Okay. Now at this point, it might be easier if you go into this double bonded bit, the methylene substituent, and draw what's there. So you have a carbon there bonded to 1 hydrogen. So 2, 4, 6, 8. There's a carbon on the end that's bonded to 2 hydrogens. Okay. This carbon here has to be distinguished from this carbon here. Both of those are atomic number 6, so we have to use the groups that are bonded to these carbon atoms. So this carbon on the dash is bonded to 3 hydrogens. Okay. This carbon is bonded to 1 hydrogen, and it's bonded to this carbon twice because of the double bond. Okay. Carbon beats hydrogen, so this group is 2, this group is 3. Okay, now at this point, you have a couple of options. Okay. All right, so let's say that this is our molecule. Okay, and I got to tip it so that I have, let me see, wait, like this, okay. All right, so the way I have this organized, and I'm going to redraw my carbon. So this is my chiral carbon, and I'm just going to draw or write the color names on the ends of the bond. Okay, so this green is the chlorine. The hydrogen is red. The dash is yellow. And the wedge is yellow, the dash is blue. Okay. Now, so you're looking at, now you can either try to look down from this direction, like coming in like this, which would make the red number 4 behind your line of sight. Or you take your model and you rotate it, so that now what you have is the hydrogen at the back. Okay, the green was 1, yellow was, 3, blue is 2. Okay, so green to blue to yellow. So this way, green to blue to yellow. That would be S. Okay, so you have 2 choices. You either, let me get a red one. you either use your eyeball here to look into the carbon like that. So 4 is in the back. Or you use a model kit and then you physically move the molecule. You can also mentally move the molecule, but it ends up trickier. Okay. All right, so I'm going to give you guys one to practice. And we can do more if you really want to, but okay. So work on that one for a few minutes. Oh gosh, you don't have to name this one because you have to name it differently because of this pi bond. So an alkene gets higher priority than an alkane. So this, I can name it, but you won't have to do that right now. So we said it was S. So 1, 2, 3, 4. 1, 2, 3. 3. So it would be S 3 chloro 1 butene. Yeah, you won't have to name them if they're if they have pi bonds in them yet. And like this one, you wouldn't have to name because I think the thiol is a higher priority. It'd probably be like 1 hydroxy. I don't know. I'd have to look it up. Okay, does anybody need more time on this one? Okay. So what you don't have drawn is the dash hydrogen. So that's 4. Okay. Sulfur has a higher atomic number than oxygen. So this is 1. But oxygen has a higher atomic number than carbon, so that's 2, and this is 3. So it's already lined up properly with the 4 on the dash. So if you go 1 to 2 to 3 like this, it ends up R. Do you want to do, oops. Okay, you want to do one more on your own? Sure. Okay, so then the purpose of the model is if you have a compound like this, where the hydrogen is not on the dash, the number 4, in order to use the clock or the steering wheel, you have to look at the molecule so that number 4 is in the back. Okay, so red. So the molecule looked like this. So if you were able to, in your brain, look at the carbon atom from a direction that's 180 degrees away from the red, you wouldn't have to move the molecule. Okay. The only reason why these colors are what I have is I just picked them. It doesn't matter what model I pick. I could have the other enantiomer. I would just end up with different colors assignments. And I just lined it up so that I have red, black, and green to be in plane. So hydrogen, carbon, chlorine are in a plane. The bond coming at me is yellow, so that has to be the wedge. The blue is going away from me, so it has to be the dash. So now instead of trying to look at the molecule in my brain 180 degrees away from the number 4 priority, I can turn the molecule and look at it head on without having to do it mentally. Like it's physically in front of me with the red at the back. So then when I assign my colors, their priorities from the actual molecule, then I just have to connect green to blue to yellow. And so I'm going in this direction, which is counterclockwise, so S. Okay. All right, so let's do one more and then we'll wrap it up for today. I'm gonna erase this bit. Oh, well, not wrap it up, wrap up new stuff. What is the name for the practice question? This one down here, Annie, you don't have to name it because you have this is gonna be some sort of file, and I don't remember, it'd be like 2-hydroxy, 1 R1-hydroxy, 1, I think like propylthiol or something like that. You don't have to name those. Okay. It's only if they have alkyl, plain alkyl, a couple of small branched alkyls, and the halogens that you have to be able to name it. So why don't you do this one where you do priority and get R and S and try to name that. Okay, does anybody need more time? Okay, well, let's do it together then. All right, so hydrogen is 4, lowest priority. Iodine is 1. The chlorine would be 2. The alkyl group 3. Okay, now again, just pick a molecule that matches. All right, so yellow, blue, green, red. Okay. Turn it so that 4 is at the back, and now we're going yellow, blue, green, yellow, blue, green. So this one is also R. Number your chain. Now you have to number the chain for naming. 1, 2, 3, 4. So this would be 1 chloro, 1, oh wait, no, R. 1 chloro, 1 iodo, butane. Okay, are there any questions before we stop 5 for today and move into a review? Oh. Karen, you're wise. Let's see, what do we got here? Oh, it's at 88, but maybe it was on Zoom. It was on maybe it was muted.
Can you hear me?
I can. Maybe I was muted. I don't know. I can hear you now.
Great.
Sorry. My fancy internet machine is smarter than I am. Okay, so are there any stereochemistry questions before we go to the review? Okay. All right. So the first question that I want to address is a little bit about the resonance. So what you need to be looking for is you have the 5 patterns. So you could have an allylic carbocation, an allylic carbanion, atoms with differing electronegativity. So one of these is rule 3 and the other one is rule 4, but they're reverses of one another. And then you have conjugation in a ring. So those are the 5 things you're looking for, but they could be just this small, or they could be part of a larger compound. Okay. So, let's see. So for example, I can't remember which ones I did and which ones I didn't. So let's draw this compound. Oh. Okay. All right, so you have a couple of different patterns in here. You have adjacent atoms of differing electronegativity. You have opposite charge separation. and you have the conjugated pi bonds in a ring. So to draw an equivalent resonance structure, you could just draw within the ring and not do anything up at the top. Okay, now one thing to note is that on these line bond structures, you don't have to draw the lone pairs. So I'm going to erase it afterwards. So this thing here is the same as this. Okay, I'm not drawing my lone pairs, but I have my charges labeled. So I don't have to draw the lone pairs. They just make it a little bit more easy to see. Okay, but so if I hadn't included the positive charge here, then the whole structure is wrong because this nitrogen is making 4 bonds. But if the plus sign is there, if the minus sign is not there and you're still implying that there's 3 electron pairs there, then it's wrong. It has to have the negative. So don't panic if you see Lewis structure or line bond structures without lone pairs. They're still there. They just don't have to be shown. Okay, so this is structure A. I drew arrows on B, on A, and I made B. Right? Now I can do some more. Now this isn't necessarily going to make a great Lewis structure, but it's possible. And since I didn't do anything in B down here, I have to leave the ring as is. It's still, this one is neutral, this one is neutral. Now this is not a good, it's not a major contributor. This would be considered non-significant or insignificant because nitrogen, if it doesn't want to have a plus charge, it's certainly not going to want to have a +2 charge. But still, I can draw it. The other one I can do, I'm going to have to redraw and get back to B. Down and up. Like that. So there's a lot of options. But you just have to make sure that whatever you have first and the arrows generate what you have second. But these are the things that you're looking for. And they can either be, there can be one pattern, there can be multiple patterns. It can be a little molecule, it can be a big molecule. There's lots of different options. Okay. All right, I think it was Thomas who asked about that by email. Thomas, does that help a little bit more with resonance?
Yes, it does. Thank you, Dr. Walters.
You're welcome. Okay. Okay, Carter's question is the practice, wait, okay, so there are 2 practice tests on Canvas. There was that little 5-question thing to get used to taking an exam on Canvas, and there is an old exam from a different semester. Which one are you talking about, Carter? Yes, the old exam is always an excellent way to prepare. So, but you're never going to, it's unlikely you'll see the same questions twice. So you're more likely to see the same type of themed thing. So let me share just real quick. Oh, that's so much crap. Open. So down here in practice exams and keys, this was from last summer, and we were in person. But if you look at it, you're like, okay, so the first question is, it's about boron, but it's, do you understand ground state electron configurations? Do you understand electron configurations of atoms? If you can say yes, then you're good on this question. If you don't, then you should review it. Okay. The second question is, do you understand Lewis structures? The actual molecule doesn't matter. It's just, can you judge Lewis structures? Okay. The third question is about hybridization. The fourth question is about functional groups. The fifth question is about molecular orbitals. So I guess what I'm trying to say with that part of it is the specific question doesn't matter. It's what is the question asking about that matters. So if you understand what these questions are asking you and how to answer the question, the thought process, then the specific question won't matter, and then you'll be fine. All right. Uh-oh, where's my other stuff? Okay, let me go back to that mass spec question then. Okay, oh, okay, so the other thing is in the summer, last summer, we gave the exams during lecture, so they were a little shorter. Practice respondus test. Oh, I should read your whole question before. See, classic example. Read the whole question before you start answering something. Okay. Mock test 1. Oh, there were 10. Okay, so this, let's see. Okay, let me go back to this. Oh, no, it's right there. That's what I wanted to show you. Okay, so when you have Newman projections, they will be labeled in some way, because the Newman projection, like this Newman projection, is built using a program called ChemDraw. So they're eclipsed. They can't draw them quite as tight as I tried to in lecture. So this is the eclipsed version from ChemDraw. They'll just look a little bit different. Flip. Oh, this one right here?
Yeah, that's the one.
Okay. Which molecule is responsible for the M+ peak in the mass spec? Okay, so this one, the place to that I would start would be by looking at, so your M peak is this one at 112, but it's 3 times as tall as the peak at 114. So having a 3-to-1 ratio of peaks that are 2 mass units apart means that the compound contains chlorine. So if you look down at your options, you only have one molecule that has chlorine in it. That's literally all you would have to do. The other thing you could do then, the other way to approach it would have been to add up determine the molecular formulas of these molecules and see if any of them are at 112. But the easiest thing to do is to use the ratio of M and M plus 2.
Okay, thanks.
Yeah. Yes, Anna, I will. Can I go over the, okay. Okay, so let's see. Okay, now over here, this one has a nitrogen in it. So nitrogen would have to have an M peak with an odd mass. One nitrogen will have an odd mass in the mass spec. This little thing here at 113 is due to the carbon isotopes. If the molecule had had a bromine in it, then M and M plus 2, these two peaks would be the same height, or approximately. It's like 51-49, but they're really close. Okay. All right, so let me go back. Annie, was your question on the Newman projection from this practice, this one here, 6? Oh. This one? Okay, so what I would do first is I would make sure that you have the same number of carbons in the compound as you do it shown in the Newman projections. So this has 1, 2, 3, 4, 5, 6 carbons in the chain, 7, 8 carbons as 8 carbons total. 6 are in a chain, 2 are in substituents. So then 1, 2, 3, 4, 5, 6, 7, 8. That one is still a possibility. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yes. 1, 2, 3, 4, 5, 6, 7, 8. Yes. 1, 2, 3, 4, 5, 6. So this one would get thrown out because it doesn't have enough carbons. Okay, so the dot is a carbon, the big circle is a carbon, and then you count everything else off of it. So 2 in the Newman projection, 3, 4, 5, 6. Okay, so the last one in this orientation is out. Okay, so when you're looking at a Newman projection, and you're looking at this carbon 3, when you see the dash means to the left of what you're looking at. So you're looking at carbon 3, you need a methyl to the left, and you need an ethyl straight down, so yes. But the other group on 3 that should be coming out to the right is a hydrogen. So this one is wrong because this has an ethyl coming out to the right. Okay, so you need an ethyl straight down, a methyl to the left, a hydrogen to the right. So this one is still okay. Ethyl down, methyl to the left, it should be a hydrogen to the right. So that's wrong. So you don't even have to go to the carbon at the back. This is right. Just by counting to get to the right number of carbons and analyzing the relative placement off of the first carbon. But, I mean, you could continue the analysis from carbon 4, that's the circle on the Newman projection. You want an ethyl group up. Here's your ethyl group up. Your methyl is on a wedge, so it's going to the right. So it's back here. And then the group that's not drawn is a dash, which would be to the left, and you would have a hydrogen. Okay, but yes, the other thing you can do, you are allowed to use your model kits. So you could build this and turn it and look at it. It takes time, but if I were you, and you have a model kit, I would make a propane with your model kits and a ring, a cyclohexane ring, and then you can add substituents on those skeletons if you need them, but have the base stuff. Okay, use my highlighters on the test to draw stuff out. You mean your computer will let you highlight on the screen? You can have a whiteboard out, you can have pencils and paper out. You don't have to do this stuff in your head. Draw it out, that's fine. What you cannot do is use a secondary device to Google search. You cannot use your book, your notes have to be put away. It's an honor system, and then the respondents will mark. But yes, you can write all over however you want to do it. You can, yes, you will have a periodic table. So the way that the exam is set up is like on the top here, you'll see one question at a time, but on the top of every question is a periodic table. It's small, but really all you need is to be able to, like with mass spec, you're just using like whole numbers. So you need to know that carbon's whole number mass would be 12, nitrogen would be 14, oxygen would be 16, hydrogen is 1. So you don't need a lot of detail from the periodic table for this type of exam.
Are we allowed to use a printed out periodic table as well if we would like,
Yeah.
or only the online
Yeah.
one? Okay.
Yeah.
Just as long as we show it to the screen ahead of time?
Yeah.
Okay.
Really, to be honest, I don't really think even the fanciest periodic tables that have a whole bunch of information on there, I don't think you need 99% of you just need the symbol, the atomic number is pretty much it, and relative placement, I guess, for us, and just, yeah, like the relative placement to get a trend in electronegativity. You don't really need much more than that.
Thank you.
Yeah, you're welcome. Okay. Yes, you just, anyone you want is fine with me. Okay. All right. All right, so the next question was about something on the old practice exam. Are there any other questions any other things about the mock exam? Any other questions that you wanted to go over? I can always come back to it. It's not a big deal. The IR. This one. Okay. All right, so which of the following molecules is consistent? Okay, so it's harder on this screen. I mean, I can annotate, but I don't know if you can while you're doing the exam. But so 1,500 and 3,000. And then single, triple, double. Okay. So you have a carbon double bonded to an oxygen. Okay. The other bonds that you'll see in the double bond region, or you could see, are carbons double bonded to nitrogens or carbons double bonded to carbons. But the most intense feature is going to be carbon to oxygen, because that's the most polar bond. So when you do a bond vibration, you're stretching the bond in and out. So as you're stretching a polar bond, you're changing the magnitude of the dipole moment. which is like a numerical measure of the bond dipole. So the carbon to oxygen bonds, it changes that dipole moment the most. So you see a really big stretch. And then these over here are sp3 carbons to hydrogens. Oops. Okay. Then what you need to consider is, let me write it over here, which functional groups contain carbonyls. Carbonyl is carbon double bonded to oxygen. Okay. So that's what you're getting down to. And so you have carboxylic acids, ketones, aldehyde, and esters. Okay. All right, it can't be a carboxylic acid because it doesn't have a jaggedy OH stretch. So ketone, aldehyde, ester. I'm gonna have to clear this stuff, but I can undo it and come down to see my list. Okay, you only have one that has a carbonyl. Now this carbon to oxygen, the single bond network, that's going to be over here, which you're not responsible for analyzing. But if you know you have a carbonyl, then you have to pick out a carbonyl containing compound. It just can't be, in this case, it can't be a carboxylic acid because of the lack of the hydroxide stretch over here. But in this kind of question, a ketone and an ester can't both be the right answer. They can't both be an option. Because for this type of question, they're both right. Ketone versus an aldehyde. No, I mean, we didn't really go into enough difference. I don't feel comfortable with that kind of a question. Sometimes it's really hard to tell them apart. Sometimes it's easier. It all depends on how easy it is to see that carbon to hydrogen stretch in the aldehyde. And frankly, it's more important that you can distinguish a ketone or an aldehyde from a carboxylic acid. Now, the other thing that you have to be careful with, let me switch my screen real quick. Is if you have a carboxylic acid like this, okay, that's not the same as this, because this has a carbon that is between the carbonyl and the hydroxide. The carbonyl is connected to the hydroxide. So this is a carboxylic acid. This is called a keto alcohol because it has a ketone here separate from an alcohol here. Whereas this whole group is the carboxylic acid. So you have to be really careful about that. This one, the IR will have, it'll have a jaggedy, broad hydroxide stretch, and then it'll have the deep carbonyl stretch. This one is going to have a broad, smooth alcohol peak, the sp3 carbon to hydrogen peak, and then a carbonyl peak. So they're going to be very distinguishable in the IR. And the difference is just a single carbon CH3 group that separates the ketone from the alcohol. Okay, so let me go back to the...
I have a question regarding this question,
Yeah.
I guess. So if you go back to the actual quiz itself, So there's one with one of the selections is a single bonded oxygen as a double bonded. Would that appear? I guess how would that appear? Would that appear to the left?
This?
Like, no, I'm sorry. Like back on the I think it was C, selection C. Oh, I'm sorry. No, it didn't have an oxygen, but on selection C. So this how would that? Yeah, how would that present? Would that be to the left?
Well, it would be in the double bond region is small. It's somewhere between like 16 and 1850. So it's going to be right in here. It's just not going to be as deep. You can't do it where, like, you say, you shouldn't do it where you say this is clearly 1750, and therefore all carbons double bonded to oxygens will be at 1750. That's not how it works. Somewhere within the region from 1600 to 1850 wave numbers, if you see a very deep, intense feature, then it's a carbonyl. If you see a feature between 1600 and 1850 wave numbers that's not intense, but maybe small, maybe only comes down to about here, then it would be a carbon-carbon double bond. Carbon-nitrogen double bond will be a little bit deeper. It's like mama bear, papa bear, baby bear.
Okay.
Okay. They're all going to be in the same region. They're just not going to all look the same. And since carbon, like this bond here, you would see this carbon to carbon double bond stretch. It just wouldn't be this pronounced. It would be shorter.
Okay.
And then here, the other thing, oh, go ahead, Andrew.
No, go ahead. Continue.
Okay, the other thing to consider is that not only on this compound do you have a carbon-carbon double bond stretch, but you have two hydrogens here. So you would have to have an sp2 carbon to hydrogen stretch for that hydrogen and this hydrogen here. My plumber just showed up. I might have to go and talk to him just a minute. You have a hydrogen here. Okay, so you would have to have, but if you look back up at your, at the IR, you don't have those stretches over here. An sp2 carbon to hydrogen stretch would be probably like right here.
Okay.
Okay, I need 2 minutes and I'll be back. Okay, thanks guys, sorry. All right, Andrew, did that answer your question about the double bond?
Yes, it did.
Carbon double bond? Okay.
Yes, thank you very much.
Yeah. Okay, so the last one that I remember somebody asking about was the old exam. Okay. Yes. Okay, so what was the first 12? I think it was 12 on the old practice exam. Okay. Oh, okay. All right. So the first thing to do with these is to read the name, okay? And just in little bits and pieces, okay? So the first thing I would do is I would look at the relative placement of the groups off the ring, okay? Which, based on this, is telling you it's trans. And then I would come down and I would underneath them, or on your paper, write, okay, so this is down, up, so that one's trans. This one is down, up, trans. C is cis. D is trans. Okay, so that's the first thing that I would do. The second thing I would do is I would look at the part of the name and find that it's a 1-3 substitution. Okay, so let me come back out here. So this one's out, 1-3, this one's out. This is 1-2. 1, 2, 3, 1, 2, 3. Okay. Then look to make sure you have an ethyl, ethyl, methyl, methyl. Okay, so now you're down to only comparing 2. Ethyl is the larger substituent, so you're going to want the largest substituent in the equatorial position. So largest group equatorial. This has largest group axial. So the lowest energy configuration is A. Okay. So, and I think, and this is a good example of like, just when you approach your exam, read the question first and figure out what information is being given to you in the question that will help you narrow down your selections. Because one thing that we've had like in the past is like people getting stuck here between A and C because they both have the substitute, the ethyl group equatorial. But you've missed the 1-3 substitution pattern instead of analyzing the 1-2 substitution pattern. So I think if you read the question and try to pull as much information out as you can before you look at the options, the better you're going to be. So again, like this first piece of information, you get something from this and you get something from this, and then combine them. It makes the question much, much easier.
Okay, thank you so much.
Yep. Okay, so number 5, because usually, especially, usually it's the littlest thing that catches people and then they get frustrated. Oh, let's see, 5. Okay. All right, so in this question, butadiene okay, which diagram below correctly represents the molecular orbitals and electron configuration of the pi orbitals of butadiene? Okay, so this is a conjugated system. So you have double bond, single bond, double bond. I'm surprised that these are here. I think these should not be here, these 3 lines up here. The resonance structure for butadiene would look like this. Okay. So you'd move these. Oh, I don't know if I can do a curved arrow. It's going to look like crap, but I'll try. here. Huh. Pitiful. And here. You can't draw it into space there. That's not too bad. Okay. So then like I said, these don't, I think we must have changed this because I know those weren't here last year because you only have 4 atoms participating in resonance. You actually need more lines. You need 4 lines. We're missing some. That's what it was. We ended up with lines here, here. We had them draw them. That's right, like that. So 1, 2, 3, 4 atoms participating. So you get 4 molecular orbitals stabilizing 1, 2, 3, 4 electrons. So the answer is D. Yeah.
I have a question.
Sure.
Could you just talk about, maybe explain the difference again between the bonding molecular orbital and anti-bonding molecular orbital, and like the HOMO and LUMO terms for the—
Sure, but I'm going to have to go to the whiteboard. But that's not a big deal, but yes, I can do that. And it's really just, what's the word I'm looking for? So if you, I don't know what the word I'm looking for is. Okay, so if you have 2 molecular orbitals, okay, the lowest one is going to be called bonding. The higher one is going to be called anti-bonding. Okay, and the difference is, and it doesn't matter if they have electrons in them. Bonding molecular orbitals contribute to bonding, which means that they like add to the bonding of the compound. Anti-bondings take away from bonding. Okay. There's a formula that you can use where you could say, why does helium never form a diatomic compound? Okay. And in this case, this is the molecular orbital diagram because you would have helium, oops, 1s2, helium, 1s2. So this would be the adding 1s plus 1s. This would be 1s minus 1s. But then when you put in the 4 electrons, you would have this. Okay. Then what you do is you say the number of anti-bonding electrons minus the number of bonding electrons divided by 2 will tell you the bond order. So in this case, you would get 2 minus 2 over 2, which is 0, which tells you that helium never forms diatomic. Okay. Actually, I had that. Bonding minus antibonding. That's what it is. Bonding minus antibonding. In hydrogen, it would be 2 minus 0 divided by 2, which would give you 1, which means that hydrogen has a single bond between it. So that's why, that's the purpose of it. But this is a little bit more than we covered. But when you say something is anti-bonding, it doesn't mean it can't have electrons in it. It just takes away from the bonding of the compound. If you would have a system that has 3 molecular orbitals, the one in the middle is called non-bonding. It can have electrons in it. It neither contributes nor takes away from bonding. Now if you have a set of orbitals, more than 3, then they don't have names at all. I'll draw them on this side. 1, 2, 3, 4, 5, 6. Then you just label them with wave functions. Okay. So 2 is bonding and antibonding. 3, bonding, non-bonding, antibonding. 4 or more, just give them a number. Okay. Regardless of how many you have, the highest energy electron that, sorry, the highest energy molecular orbital that has electrons is called the HOMO, highest occupied molecular orbital. The one right above it is called the LUMO, the lowest unoccupied molecular orbital. The reason these are important to visualize is that, or to know where they are, is if this is your bonding situation, this energy difference is called the HOMO-LUMO gap. Okay. If the energy change in the HOMO-LUMO gap is small, the wavelength associated with that energy difference is large. And in some molecules, it can be so large that it can lead to colors in organic molecules. So if you have a tomato, it has lycopene in it. And lycopene has a HOMO-LUMO gap that absorbs the wavelengths so that are complementary to red, which would be like the, well, you'd need a color wheel, I can't exactly remember, but it'll absorb some wavelengths, it'll transmit other wavelengths. And that's why tomatoes are red, because of the HOMO-LUMO gap associated with the I forgot what I was going to say. It has to do with the magnitude of the energy difference between the HOMO-LUMO gap. But right now, we're just covering, like, could you pick out a highest occupied? Could you pick out a lowest unoccupied?
Thank you. That helped.
Yeah, good.
I got a quick question.
Sure.
So the number of arrows that go on each one of those lines is, you get that from the number of pi bonds and the electrons in the pi bonds, correct?
Or the lone pairs.
Or the lone pairs?
Yeah, so if you have, if you had an allylic carbanion, the resonance structure involves 2 pi electrons and 1 lone pair of electrons. So this is a 4 electron resonance that occurs over 3 atoms. So the number of atoms tells you the number of lines on your molecular orbital diagram. So 3 atoms, 3 pi, or sorry, 3 p orbitals make 3 molecular orbitals. So there would be a, if you drew this out, you would have a pi bond here, a pi bond here, and a pi bond here, all contributing to stabilization of these 4 electrons. So 3 atoms, 3 p orbitals, 3 molecular orbitals, and then you put in the molecular orbitals the 4 electrons. If it was an allylic carbocation, you have 3 atoms, so you're going to have 3 molecular orbitals, but now you're only stabilizing 2 electrons. Because this resonance only involves is a 2-electron resonance over 3 atoms. So the atom number tells you the number of molecular orbitals. The diagram tells you the number of electrons shared or distributed. Does that make sense?
Yes, thank you.
Okay. Are there any other questions? Okay, if there aren't any other questions, I'll be around most of the day, I think. Obviously the plumber's here, so I can't really do too much. So if you need anything between now and when you take your exam, let me know. Make sure you do have to, I just found out last night, you do have to download Respondus. So that should be available on the UNCW website. But if you have any questions, I'll be here definitely at the computer at 4 in case there are any problems. Good? All right, well, good luck, everybody. And I will, if I don't hear from you today, I will talk to y'all tomorrow. Okay? All right, good luck, everyone.
Thank you.
Yeah, you're welcome. Talk to you soon.
Have a good day. Thank you.
Thank you.